Dear colleagues, my name is Igor Kulikov. I am Doctor of Science and Senior Researcher of Institute of Computational Mathematics and Mathematical Geophysics, Siberian branch of Russian Academy of Science, Novosibirsk, Russia. Talk and title of my talk, New Code for the Numerical Simulation of Relativistic Flows on Supercomputers by means of a low dissipation scheme. Outline of talk have 5 points. We need to new efficiency codes, of course, for new architectures of supercomputers, the new numerical solver for new codes, of course, verification of this code, relativistic jet simulation, and conclusion. The universe is a very interacting measures and dynamic systems. By example, white dwarf measures, neutron stars collision, relativistic jet, and black holes interact. Of course, for numerical simulation of these phenomena, we need to new numerical method, efficiency numerical solver, and we use top supercomputers for numerical simulation. In this slide, you can see a very interesting trend in supercomputers from supercomputers Blue Gene by Jaguar, Tianhe-2, and Summit. Red circle is the nodes of supercomputers, and blue stars is a number of cores in one node. On next slide, you can see dashed lines, and this line cross in this point around 2000 nodes and 2000 cores in one node. Maybe is the architecture of supercomputers, but we have trends in supercomputers and numerical codes. What is the trends? Of course, is a decrease of MPI processes, minimize of MPI communications, increase of computational threads, exchange from OpenMP technology to POSIX thread technology, or exchange high-level technology for threads to low-level threads. By example, in POSIX threads, or maybe in C++ standard. Using vectorization intrinsic, SIMD, SSE, AVX, and other technology. And today we need to the architecture-oriented codes. Okay, what is the numerical solvers for relativistic hydrodynamics? In this part of slide, I write special relativistic hydrodynamic solver. For numerical solution, we can solve. We can use Godunov method in standard form, and in third part of this slide, you can see flux for Godunov method. What is the feature of this flux? Main feature of this flux is the vectorizable of all operation. And in this flux, we can use piecewise parabolic, piecewise linear, piecewise cubic, or generally piecewise polynomial function for reconstruction of flux and solution. It's very important for construction of high-order numerical methods. Of course, these polynomial functions were safe vectorizable in numerical methods. And in the parallel code, we can use all decomposition, all domain decomposition. Geometry decomposition by means MPI technology, and threads decomposition by means OpenMP and POSIX threads technology in work join idea. And on low level, we can use vectorization by means of AVX technology. On this slide, you can see example of vectorization of flux computing. This is flux of the Rusano flux or Lux Vendrov flux. Okay, what is the scalability of a numerical method? The weak scalability or efficiency is on 16 kernel processors, Intel Xeon Phi kernel processor, around 96% is very high. Speed up or strong scalability around 50 factor is a very good result for Intel Xeon Phi, and around 200 gigaflops on one Intel Xeon Phi kernel. Small or big 6 gigaflops. This code fastest in 20 factor if compared with classic code on CPU. Of course, we need to verification of the code and numerical method. On this slide, you can see a standard problem of blast wave with tangential velocity is the density, pressure, normal velocity, and tangential velocity. This numerical method is a low dissipation numerical method on discontinuities and high order method on differential solution. Of course, verification of numerical method on Kelvin-Gilgoy's instability on this slide. Verification on two-dimensional blast wave test. Domain divide to for domain northwest, southwest, southeast, and southwest zones interact to form contact discontinuities with a jump in the tangential velocity. This contact discontinuities yield numerical artifact in the SV zone. Note that is the less pronounced in the implementations based on the piecewise parabolic methods. The formation of two interactive shock waves causes a density spike in the NGR region. This zone is also present in some of the PPM implementations. Note that some cases of breakdown of discontinuity have been thoroughly tested in one-dimensional test. Therefore, only the interaction of discontinuities are considered here. Okay, and next test is a two-dimensional Emery step problem. The Emery state test is to simulate the running of a relativistic gas flow on step. The test is only synthetic, since in real astrophysics there is no step that called Winston the relativistic gas flow. I don't know, maybe if Superman or Batman, I don't know. And the gas collides with the step spherical shock waves moves on the opposite direction. The reflection forms the upper boundary take place in the form of a straight vertical stem. From the stem base in the spherical reflect shock waves, this moves on another discontinuity, which is reflected from the stem. Note that although there are boundary artifacts near the step, they do not affect the global flow in the test. And multi-dimensional, one-dimensional, two-dimensional, three-dimensional blast wave test on this slide. We simulated relativistic galaxy jet, and full structure of relativistic galaxy jet is the shock front is here, shell, hotspot point here, contact surface, cocon, of course jet, and two a very interesting flow, Kelvin-Gilgoy's instability here, and backflow of galaxy jet. In conclusion, a new efficiency, high-order numerical method, a new parallel code on base MPI OpenMP AVX technology, and numerical simulation of extragalactic jet structure. Thank you to the Russian Science Foundation, and thank you for attention. Thank you very much. And in these slides, you can find some information about me and my last publication. Thank you very much.